Okay, 1.2. 1.2, we're going to still be looking at this domain and range and looking at pictures, still continuing with that interval notation that we have. So on page 1 of 1.2, when you have this picture, we do want to consider all these highlighted open line points that we have here. We want the domain of this picture, of this function. Well, the domain are the x values. So the x values are going to go from that point left to right. And that point is going to be to -4. And then notice the picture does go continuously all the way to 1, 2, 3, 4 to 5. Now when I look at a closed circle means we are touching it. It is inclusive. And an open circle means we're not touching it or not inclusive, and that's why it's going to get a parenthesis. On part B, it says find the value when x is -1. F of -1 means that is my x value. So when I'm finding a value, I'm finding a y value. And that's pretty much always going to be the case. If you're given x, you find y. If you're given y, you find x. So in this case, I'm given x is -1. Well, -1 is here. So what is the y value? That y value, f of -1, that y value is approximately, we're going to say, 2.5. So when I do f of 2, then I come over here when x is 2, here's 2. What is that y value? Well, that one's easier. It's right on the line. We say 3. So what is the range? The range is the y values. That's how high and low does the picture go. Well, the lowest point is here. The highest point is all the way up there. So when I put together my range, I'm going to say that it goes from -1 to 4. Now we always go in order from smallest to biggest. And at -1, I look at the point. I am touching it, so it is inclusive, bracket. And then I go up to my highest point, and it is touching it. So a bracket is going to be used on that one. Find the domain and range of f of x equals x minus 3. Okay, so when it comes to this picture, we can put it in our calculator. And when we put it in our calculator, we're going to get the square root of x minus 3. And there's our picture. Notice that it actually starts at +3. 1, 2, 3. And it goes up. This is just a slight introduction to where we're going to start moving things that we've talked about with that whole HK of moving absolute values, moving square roots, and moving things. This is kind of a notation to that. Notice a -3 means it actually starts at +3. So what is the domain? What are the x values? Where does it start and how far left and right does it go? Well, the domain is from 3 to infinity. I get to touch 3 and not infinity. And then the range is how high and low does the picture go. Well, it starts at 0 and it goes to infinity because that picture is going to keep going, keep increasing. I get to touch 0 and I never get to touch infinity. So that's going to be how we find the domain and range of a picture. We can use our calculator to help us out with that. Remember the vertical line test? We talked about that in the last section. If it doesn't intersect in more than one point, or if it does touch in more than one point, then it is not a function. Increasing functions, decreasing functions, constant. You should be very clear as to what's increasing, what's decreasing, and what's constant. Page 2 of the notes, when we look at a graph, y equals x to the fifth, we're going to sketch this here. So we're going to go to our calculator, y equals x to the fifth. And we're just going to do a very quick sketch of it. It's really not a, too complicated. If I'm unsure what's really happening here, I could change my scale, my y's. Perhaps I just want to go -3 to 3 by 1/2, and that would spread things out a little bit. And notice that it just looks like it's still curving through the origin. It's not really doing anything else through there. So that's just a quick sketch of it. And we would say, is this graph increasing, is it decreasing, or is it constant? And you should be able to clearly see that it's increasing. Over what interval? Well, it starts increasing at -infinity, and it keeps going all the way to positive infinity. Graph y equals x cubed minus 3x. Alright, so x cubed minus 3x. When I graph this picture, I'm just doing a quick sketch of this. Notice that we do have some change points, so we do want to be a little bit more specific. It does give us that information within the note packet here at -2 and at 0 and at +2. It looks like it's coming up in between here, so something like this. Alright. So we say this function is increasing. So where is it going upwards at? Well, this is all upwards. Up and up. Upwards. Even though the arrow is going down here, it's still from the negative. We read from left to right. It is going upwards. So we would say from to that point, because at that point it starts to go downwards, and from that point it starts to go again upwards. So we'd say from -infinity to 1, because we always go off of x values, always x values, and from +1 to infinity. Again, we're only looking at our x values. So where is it decreasing at? Well, it's decreasing between those two, from -1, from -1 to +1. So it's increasing up to the x value -1, then it decreases from the -1 to +1, x values, and then it increases again from the x positive value all the way to infinity. If we would have done this with our interval testings, it would have looked the same way. It would have gone from positive negatives from that aspect. The point at which a function changes its increasing, decreasing, we call these relative maximums and relative minimums, because there's sometimes more than one of them, or there might be a combination of them. Unlike a parabola, there's only one change point. Anything more than a parabola, a cube, a fourth, a fifth, will have more than one. Therefore, we call them relative. And that's what it's talking about there. The next part, make sure you read through this, considering what relative minimum, maximum. Using your graphing calculator, we want to approximate the relative minimum and maximum for that equation that is given. Put it in our calculator here. So we're going to go y equals 4x squared minus 3x minus 2. We're going to graph it. Okay. I have a different window, so I'm just going to make sure we're seeing everything. So I'm going to go zoom 6. I'm going to zoom out a little bit. It is a parabola because it's a square, so we do see all of our important pieces. So the only thing that we really care about is that minimum and that maximum. And that minimum, there is no maximum in this parabola. So second, calculate. And then we're going to go to a minimum. And then it's going to give us our flashing spider, and we have to be to the left. Then you have to be to the right. And then you just hit enter. So to the left, move the spider to the right. Are you sure? Yes. We've done these several times by now. And now it says round 3 decimal places. So when I look at this, the relative minimum is at 0.375, negative 2563. So just follow directions, use your calculator, and go from there. All right, page 3. This is called a step function because it looks like stair steps. A piecewise function because the picture is cut into pieces. So that's all it's asking you to do is you need to be very familiar with the look of a step function, the look of a piecewise function. More specifically with this piecewise function, we're looking at the line 2x plus 3. So you would normally go, okay, there's 3, and I rise and I run. So that's my line. But we're cutting the domain off at 1. That's why it stops there and does not continue like we normally would. Same thing with the plus 4. So there's the 4. And it's going down and over, down and over, down and over. So generally, we would have had, a whole line. But because we only want the domain from 1 and greater, that's the only part of the picture we're looking at. So yes, there are other parts of the picture, but this domain is only making us look at a piece of the line rather than the whole thing. So those are just getting familiar with what is a step function look like, what does a piecewise function look like. Okay. On page 4, we've talked about these symmetries, and we talked about this even and odd when we talked about reflections of points back in, I think, section P1 even. So if it is symmetric with the y-axis, then we say that the graph has an opposite x value and the same y value. And this is what we talked about. If this was a reflection over the y-axis, this was the point we had. So if I'm over the origin, both of them were negative. And if I'm over the x-axis, then I had a y that was negative. So when we talk about this symmetry, when we reflect over the y-axis, when we reflect over the origin, and when we reflect over the x-axis, we have what's called these odd and even functions. If you're symmetric to the y-axis, you're an even function. If you're symmetric to the origin, you're an odd function. And if you are symmetric to the x-axis, you're not even or odd. You're neither. Now, that's just the wording, even, odd, or neither. Then we have the computation part. If you are even, symmetric over the y-axis, this relationship is going to be true. The x and the opposite of x are going to be the same. However, if you are reflective over the origin, this relationship is true. The opposite of x is the same as opposite of y. Because remember, f of x represents y. The opposite of x is the opposite of y. So you need to kind of know those two relationships as it relates to y-axis and x-axis. So let's look at these 4 examples, and we're going to talk about, is it odd or even? We're going to sketch the graph, but also show it algebraically. So an absolute value of x, hopefully we've gotten that it's a v. If you don't believe me, go ahead and put it into your calculator. All right, and now we're going to, we should visually be able to see that it does reflect over the y-axis. So visually, we can see it reflects over the y-axis. But we need to be able to, which means it's going to be even, but we need to be able to prove it algebraically. So if that's the case, if I go f of negative x, that means I'm replacing x with negative x. I replaced x with the negative x. I'm doing that substitution. Then f of negative x is the same as x, because the absolute value of a negative is a positive. Therefore, f of negative x, because I haven't changed anything over here, is, well, what was x? X was the same as the original f of x. I've proven it algebraically that it is even. F of negative x is f of x. All right, let's try it again. Let's come over here to b. Graph it. We're going to get something looks like that. It's a cubic, some kind of S shape. So the first thing I have to do is I'm going to prove algebraically. So that means I'm going to replace the x with negative x. That means I replace the x with negative x. Well, a negative x cubed is still negative x. Negative x cubed. And now I have negative negative, which is plus x. So now I'm going to take that negative out, and so I get x cubed minus x. Well, x cubed minus x is the exact same as my original function. So I have a negative of my original function. If I come back up here, if I put in the negative and I get a negative of my original function, put in negative, I get a negative of my original, then it's odd. And if I look at my picture, yep, what's on the first quadrant is flipped over into the third quadrant. It is reflective over the origin, therefore it is odd. Let's try it again. X squared plus 1. We're going to first just look at it algebraically. So I'm going to change x to negative x. So I'm going to change x to negative x so that negative x squared is x squared. H of negative x, well, x squared plus 1 is h of x. So the negative gave me the original. It must be even. When I put this into the calculator, I'm going to get a parabola, something like that. And again, we should see that, yes, it reflects over the y. Okay, one more time. First of all, algebraically, I'm going to substitute in a negative x. Negative x. Negative x cubed is still negative x cubed. Well, if I try to take out, now this is not f of x, so that is not even. So I'm going to try taking out the negative, so I get x cubed plus 1. Well, this is not the negative of the original function. This is not the original function because of the plus and minus sign. So therefore, this is neither. This is actually reflective over the x-axis, and if I graphed it, x cubed minus 1, let me just show it to you here. Let's see. There we go. X cubed minus 1. We get that it doesn't have to be reflective, I'm sorry, over the x-axis. It's just is not odd and it's not even. But there's my picture, because it does not reflect over the y, and it does not reflect over the origin. So it is neither, and we prove algebraically that it is neither. All right, so that will take care of 1.2 for us.